Imagine this. You've got this brilliant AI, maybe machine learning idea. You've even got it working in a proof of concept humming along in a Jupyter notebook. But then you hit the wall. How do you take that little spark and turn it into something real, something robust, scalable, secure, actually running out there in the cloud? That jump from the lab notebook to live production, it's a massive gap. And honestly, it's where a lot of great ideas just stall out. So today we're doing a deep dive specifically aimed at bridging that gap. We're navigating the Amazon Web Services AWS ecosystem for AI and ML, and we're basing this discussion on a really practical guide designed to give you that blueprint, that path from concept to cloud deployment.
Yeah, exactly. Our mission today for you listening is really to give you that core understanding you need to confidently build, deploy, and operate these kinds of intelligent systems on AWS. We want to provide a clear framework, some actionable insights, covering everything from the absolute foundations up to those tricky operational concerns you hit in the real world.
Okay, let's unpack that central challenge then. Because it's not just knowing what AI can do, right? Or even just training a model. Lots of people can do that now. The really hard part is architecting that whole end-to-end system. The data ingestion, automating the retraining cycles, making sure deployment is secure, keeping an eye on performance. That's a whole different ballgame.
It is. And what's interesting is how the source material calls this out as a vast and complex gap. It really emphasizes that moving beyond just playing around, beyond experiments, requires practical mastery of the cloud platform itself. It's about operationalizing AI on AWS, not just showing off a cool model. It's about building something that works reliably in the real world.
Right. So before we even get to the fancy AI and ML services themselves, the guide really hammers home this point. You need an unshakable command of the core AWS pillars. It's like the bedrock, isn't it? Without that solid foundation, whatever AI solution you build, it's probably going to be inefficient or insecure, or it won't scale, or it'll just cost way too much.
That's absolutely right. And it begs the question, what are these foundational skills, the non-negotiables that you just have to get right, regardless of what new AI model drops next week?
Yeah.
Okay, let's start with compute. The AML compute engine. Amazon EC2, ML is hungry for compute power. It's just intensive. So the choices you make here, the instance types, they directly impact everything, how long training takes, your inference speed, and crucially, how much you spend.
Makes sense. So what are the main categories we should be thinking about within EC2 for ML?
Broadly, there are a few key types. First, you've got the heavy hitters. The accelerated computing instances. Think P family and G family. The P family, with the powerful NVIDIA GPUs like A100s or H100s, those are the real workhorses for training huge models like the LLMs everyone's talking about. You can even link them up in EC2 ultra clusters for like supercomputer level power. The G family is a bit more versatile. Still great GPUs, often used for graphics too, but also really cost effective for ML inference tasks.
Okay, so P for massive training, G for versatile inference and graphics. What else?
Then there's AWS's own custom silicon. This is really interesting. AWS Trainium and Inferentia. Trainium instances, the Tron family, they're purpose-built just for ML training. The whole point is to bring down that cost to train, sometimes by up to 50%, which is huge. And Inferentia, the Inf family, is tailored for inference. High performance, low cost, especially good for generative AI models.
So that presents a big choice then, doesn't it? Go with the familiar NVIDIA ecosystem, the P&G instances, which might be faster to get started with because everything supports it.
Right, development velocity, portability, maybe easier hiring because the skills are widespread.
Or do you invest in learning the AWS custom silicon, Trainium, and Inferentia for potentially better long-term cost savings and performance?
Exactly. And that's not just a tech decision. The guide points out it has these macro consequences. It affects your MLOps pipelines because you need the AWS Neuron SDK. It might even change who you hire, right? You need people familiar with that specific tooling. It's a strategic call.
That's a really critical insight.
Yeah.
Okay, so we've got the compute sorted, or at least the options. Where does all the data live, the fuel for these models?
Good question. That brings us straight to the data-centric core. Amazon S3 as your ML data lake. Honestly, in AWS world, S3 is just the center of the data universe for machine learning. It's fundamental. It's where you put your training data sets, your model artifacts after training, config files, logs, everything. And its value for ML really comes down to two things: virtually unlimited scalability and just extreme durability.
The 11.9s thing. Right.
Yeah, 11.9s of durability, meaning your data is incredibly safe. You don't really worry about losing it. And for cost, S3 has different storage classes. S3 standard for frequent access, intelligent tiering, which automatically moves data around to save you money, and then archive tiers like Glacier for older stuff. You set up lifecycle policies to automate that.
Okay, standard cost optimization stuff.
Yeah.
What about performance? Loading data is key for training.
Right. And for that, there's S3 Express One Zone. It's designed for really high throughput and consistent single-digit millisecond latency. Can seriously speed up training by getting data to the compute faster. And here's something architecturally quite powerful. S3 Object Lambda. This lets you actually embed code, like pre-processing logic, resizing images, redacting PII directly into the S3 GET request.
Whoa, okay, so instead of pulling data and then processing it elsewhere.
Exactly. The processing happens as the data is retrieved from S3. It simplifies your application code massively, ensures consistency because the logic is right there at the source, and can save a ton of engineering headaches. It's a neat architectural pattern.
Oh, that does sound like a big win, especially for keeping pre-processing consistent. All right, compute, storage, what about locking it all down? Securing the data, the models.
Yeah, crucial. Securing your innovations. AWS IAM for AML, the guide nails it. Security is job zero. And IAM identity and access management is how you enforce that. It gives you that fine-grained control, who can do what on which specific resources. You absolutely have to design security in from the start. Can't be an afterthought.
So what are the key IAM concepts we need to grasp for ML?
The main ones are IAM roles and IAM policies. Rules are the best practice, definitely. They grant temporary credentials, so like your SageMaker notebook gets assigned a specific SageMaker execution role.
So no hard-coding access keys in the notebook.
Please, no, that's a huge security risk. Roles avoid that entirely. The role has permissions defined by an IAM policy, which is just a JSON document. And the absolute core principle here is least privilege. Only grant the bare minimum permissions needed for a task, nothing more.
Makes sense. What about bigger setups, multiple accounts?
Roles are key there too. They enable secure cross-account access and federation, so your dev account might assume a role to access specific resources in the prod account natively. And this focus on roles and least privilege is fundamental for MLOps automation. Each piece of your pipeline, the CI/CD tool, the training job, gets its own role with just the permissions it needs. It drastically reduces the blast radius if something gets compromised.
Okay, so compute, storage, security, that's the bedrock. Now let's get into the heart of it. The AWS AML services themselves. It looks like a huge portfolio, almost overwhelming. How do we even start to make sense of it all?
It can seem sprawling, you're right, but the guide offers a really helpful simplification, a clear three-layered approach. Thinking about it in these layers helps you make deliberate choices based on what you actually need, balancing speed, control, and how much customization you require.
Okay, 3 layers. Lay it on us. What's layer 1?
Layer 1 is applied AI, I think intelligence as an API. This layer is all about using pre-trained models through simple API calls. It abstracts away all the underlying ML complexity. The big win here is speed, rapid development, and integration. You get ready to use AI functions pretty much off the shelf.
So like image recognition, text analysis.
Exactly. Amazon Recognition for vision tasks, Amazon Comprehend for NLP insights, Amazon Transcribe for turning speech into text. It can even do speaker diarization and PII redaction. Then there's Translate, Poly for text-to-speech, Lex for chatbots, Textract for document analysis.
Textract seems key for that IDP stuff later.
Definitely. And Kendra for enterprise search, Personalized for recommendations, Forecast for time series, and crucially, Amazon Bedrock.
Bedrock. That's the generative AI one, right? Accessing foundation models.
Precisely. It's a managed service giving you API access to models like Claude, Stable Diffusion, Llama, others from various providers. Lets you build generative AI apps super fast without managing infrastructure. The point of this whole layer is their solution accelerators. They slash time to market for common problems, months down to days or hours. They democratize AI, basically. Developers who aren't deep ML experts can still build powerful features.
Okay, super powerful for quick wins and common tasks. But what if those pre-built APIs just aren't specific enough for my business problem?
Great question. That's exactly when you move up to layer 2. The ML platform building custom intelligence with Amazon SageMaker. When layer 1 isn't sufficient, SageMaker is your go-to. It's this comprehensive, fully managed platform specifically designed for building, training, and deploying your own custom machine learning models.
So it's like the IDE for data scientists.
It's the IDE and the workbench for data scientists, yeah. But it's also the MLOps engine for engineers. It covers the whole lifecycle. For data prep, you've got Studio Notebooks, Data Wrangler for visual ETL, Ground Truth for labeling data. For building and training, there are built-in algorithms. You can bring your own custom scripts. It handles distributed training, automatic hyperparameter tuning, even SageMaker Autopilot for automated ML.
And deployment.
Yep. Real-time endpoints, batch processing, even serverless inference for variable workloads. And critically, it has strong MLOps and governance features. SageMaker pipelines for CI/CD, a model registry for versioning and tracking, SageMaker Clarify for checking bias and explaining models. The real value proposition of SageMaker is that deep, seamless integration. It solves that horrible glue code problem you get when trying to stitch together a bunch of separate open source tools yourself. It cuts down the operational burden massively so teams can focus on the data and the models, which is where the value is.
Okay, SageMaker sounds like the powerhouse for custom ML work, handling everything.
Yeah.
Is there yet another layer for even more control?
There is. Layer 3. Frameworks and infrastructure. This is for when you need maximum control, maximum flexibility. Maybe you're doing cutting-edge research or building a totally custom ML platform. Here, you're basically working closer to the metal. You'd use things like deep learning AMIs, DLAM AIs, or deep learning containers, DLCs.
So pre-built environments on EC2.
Essentially, yeah. They come pre-configured with popular frameworks like TensorFlow, PyTorch, all the NVIDIA drivers like CUDA, ready to go on raw EC2 instances, or maybe orchestrated using container services like ECS or EKS. Think of Layer 3 as the escape hatch. It's there when you have highly specific needs that Layers 1 and 2 don't quite cover, and you have the expert team to manage that lower-level infrastructure.
Got it. So the layers represent increasing control, but also increasing complexity and management overhead.
Precisely. And connecting it back, this layered approach really caters to everyone. A startup might just use a Layer 1 API. A large enterprise might use SageMaker extensively. A research lab might live in Layer 3. A good architect understands this spectrum control versus convenience and knows exactly where their project fits and why.
And I really like that the guide includes that Rosetta Stone, comparing AWS services to Azure and GCP, knowing recognition maps to Azure AI Vision or Bedrock maps to Azure OpenAI service. That's super helpful for folks coming from other clouds or working in multi-cloud places. Really helps with communication.
Definitely valuable context.
Okay, let's shift gears a bit. Let's talk about the people involved. The guide draws a clear line between the solutions architect and the software or ML engineer. They're not the same role. So what does this distinction really mean when you're building a team? Or maybe if you're thinking about your own career path in this space?
It's a really important distinction. Fundamentally, the architect is the strategist. They're the translator, connecting business problems to technical solutions. They worry about the what and the why. They're also the guardian of the system's overall health, scalability, security, cost. The engineer, on the other hand, is the implementer, the builder. They're focused on the how. They write the code, configure the tools, optimize the performance.
Okay, let's break that down. The architect's blueprint, what are their key responsibilities?
Right. So the architect translates business goals like reduce churn by 15% into a technical architecture. Maybe that's a SageMaker pipeline feeding a real-time endpoint.
Yeah.
They do the service selection, weighing the trade-offs. Should we use Textract or do we need a custom SageMaker model for this? That's an architect-level decision. They're heavily focused on those non-functional requirements we mentioned. Designing for scale, security, reliability, cost efficiency right from the start, defining VPC structures, IAM policies, and a huge part of their job is stakeholder management and communication. They need to explain complex tech decisions to business leaders in a way that makes sense.
So, broad skills needed. Systems thinking, deep cloud knowledge, security, business sense, cost management, communication. Client leadership, too.
Absolutely. Now compare that to the engineer's build. If the architect designs the house, the engineer builds it, brick by brick. Their work is very hands-on. Implementing data pipelines, writing Python or Scala code for AWS Glue or Spark jobs to do ETL. They implement the actual ML models using frameworks like PyTorch or TensorFlow, using the AWS SDKs, the SageMaker Python SDK. MLOps automation is a massive part of the engineer's role now, building those CI/CD pipelines, using SageMaker pipelines, code pipeline, maybe GitHub Actions. And they're responsible for tuning and optimization, hyperparameter searches, optimizing code, debugging tricky performance issues.
So, deep programming skills, expert in ML frameworks, data wrangling, containers like Docker, and really hands-on with services like SageMaker, Glue, Lambda, much more specialized.
Exactly. They need deep expertise in the tools they use daily.
Can you give a couple of examples of how they collaborate across a project? The guide had a table, right?
Yeah, good examples. Take project scoping and design. The architect is defining the KPIs, drawing the big architecture diagram. Meanwhile, the engineer might be doing a quick proof of concept, maybe testing Textract on a few sample documents to see if it works well enough for part of the problem,
Okay.
or during data preparation. The architect designs the overall IAM policies for data access and S3 encryption strategy. The engineer is actually writing the PySpark script for the glue job that cleans the data, normalizes it, creates features.
So different focuses, but working together.
Completely complementary. One ensures the strategy is sound, the other makes sure it actually gets built correctly. You really need both perspectives for a successful project.
Right, that makes a lot of sense.
Yeah.
Okay, let's make this even more concrete. Let's move from the roles to a practical example that ties a lot of these threads together. The guide walks through an intelligent document processing IDP pipeline. This should show how multiple AWS AI and serverless services work together in practice.
Yeah, it's a great example. The scenario is pretty common. A company, maybe financial services, is drowning in thousands of PDF invoices every day. It's all manual, slow, error-prone, costs a lot. The goal: build a fully automated serverless pipeline, ingest the PDFs, automatically pull out the structured data, maybe classify the document type, identify key bits of info like invoice numbers or due dates, and store it all neatly.
Okay, so what does that architecture look like? You mentioned serverless and event-driven.
Exactly. It's a really elegant pattern, basically.
Uh-huh.
A PDF gets uploaded to S3. That upload event automatically triggers an AWS step functions workflow. Step functions then orchestrates a series of Lambda functions. One Lambda calls Textract to read the document, another might call comprehend for analysis, and a final Lambda takes the results, saves them to another S3 bucket, and maybe logs key details in DynamoDB.
Ah, I see. Serverless, so no servers to manage. Scales automatically. Pay-per-use. Nice.
It's a very common and powerful pattern on AWS.
Okay, let's walk through the steps. How does it kick off?
Step 1, ingestion and triggering. The front door. You set up an S3 bucket as the landing zone for the incoming PDFs. Then you configure S3 event notifications. The key here is you can set it up so a new PDF arriving directly triggers your step functions state machine. No polling, no extra glue code needed.
Very clean. Okay, step functions gets triggered. What does it do?
Step 2, orchestration with AWS step functions. This is the brain, the conductor of the orchestra. Step functions is perfect for these multi-step asynchronous tasks. Why? Because it handles state management automatically. It knows which step you're on. It has built-in error handling, retry logic. If a step fails, it can catch it and maybe try again or go down a different path. Plus, you get a visual workflow, which is amazing for debugging and just understanding what's happening. You define the whole flow using a JSON format called Amazon States Language ASL.
Okay, so step functions calls the first Lambda. What's that doing?
Step 3, text and form extraction with Amazon Textract. This is the pipeline's eyes. The Lambda function's job is simply to call Textract's asynchronous API start document analysis. And you tell Textract what you want. In this case, you'd request the forms and tables features. This is crucial. It doesn't just give you raw text, OCR. It pulls out structured key value pairs like invoice number, 12345, and data from tables within the document. That structured data is key for automation.
Right. You need the structure, not just a wall of text. What's next?
Step 4, custom analysis with Amazon Comprehend. Getting more insight. Another Lambda function, triggered by step functions once Textract is done, takes that structured output. It then sends relevant text fields to Amazon Comprehend. Here you might use a custom classification model you've trained in Comprehend to automatically tag the document, say, as an invoice versus a purchase order. And you could also use Comprehend's custom entity recognition to find specific business details you care about, maybe extracting the invoice number, the due date, the total amount, things your downstream financial systems need.
Okay, so Textract gets the structure, Comprehend adds specific business meaning. Then what happens to the results?
Step 5, storing the structured output. The record keeping. A final Lambda function gathers all the results, the structured data from Textract, the classifications and entities from Comprehend, and bundles it all up into a nice, clean JSON object. It then writes this JSON to a processed S3 bucket, maybe for archiving or feeding other systems. And it could also pull out key fields, like the invoice number and total amount, and write those to an Amazon DynamoDB table.
Why DynamoDB?
For quick lookups. So another application could easily query by invoice number to find the status or the total amount without having to parse the full JSON file in S3 every time.
That's a really neat end-to-end flow, using several services together seamlessly. But what takes it from a cool demo to something truly production-ready?
Good question. 2 key enhancements really make it robust. First, solid error handling. Step functions lets you add catch blocks to your workflow definition. So if that textract call fails or the comprehend lambda error is out, you can catch that specific error. And instead of the whole workflow just failing, you can route it somewhere else, maybe send an alert via SNS or move the original PDF to a quarantine S3 prefix for someone to look at manually.
Okay, handling failures gracefully. What's the second thing?
Human in the loop. Let's be honest, no ML model is perfect 100% of the time. So for predictions where the model has low confidence, maybe textract isn't sure about a field, or comprehend gives a low score for the document type, you can integrate with Amazon Augmented AI or A2I. A2I automatically routes those low confidence cases to a predefined human workforce for review. They look at it, make the correction, and here's the magic. Those human corrections can be automatically fed back to potentially retrain or fine-tune your models.
Ah, the virtuous cycle.
Ah,
Improving the model over time based on real-world corrections.
exactly. That feedback loop is crucial for maintaining high quality in production.
Okay, so building the pipeline is one thing, but then there are all those other concerns that make something truly enterprise-grade. The guide calls them non-functional requirements, right? Scalability, reliability, maintainability,
Right.
and definitely cost and security.
Yep. These are the IMLOPs, as they're sometimes called. Mastering these is what separates a prototype from a real production system that you can rely on. They're absolutely critical.
Let's talk cost first. AML can get expensive if you're not careful. What are the key strategies for strategic cost optimization or FinOps in this space?
It's a huge topic. First, right-size your compute constantly. Use CloudWatch metrics to monitor your SageMaker training jobs and inference endpoints. Are they over-provisioned? Can you use a smaller instance type? Downsize aggressively. Second, for training jobs that can handle interruptions, definitely leverage spot instances. You can get massive discounts, up to 90% off on-demand prices. SageMaker has built-in support to make using Spot easier for training.
Huge savings potential there.
Absolutely. Then, for your steady, predictable inference workloads, look at savings plans or reserved instances. If you can commit to usage for 1 or 3 years, you get significant discounts compared to on-demand.
What about the newer stuff, like Bedrock and Generative AI? Costs there can add up fast.
Crucial point. For Amazon Bedrock usage, be strategic. Start with smaller, cheaper models first, maybe Claude 3 Haiku. Only use the big, powerful, expensive models like Opus when the task complexity absolutely demands it. Implement intelligent routing, maybe have a simpler model try first and only escalate to the expensive one if needed. And use prompt caching. If you send the same preamble often, caching can save a lot on input tokens.
Good tips. What else on cost?
Don't forget data storage. Use S3 lifecycle policies to automatically move older training data or logs to cheaper tiers like Standard IA or Glacier. And finally, monitor everything. Use AWS Cost Explorer to visualize spending, set budgets, and use cost anomaly detection to get alerts if spending suddenly spikes unexpectedly. You need visibility.
Okay, keeping costs under control is vital. What about security? How do you harden these ML systems?
Security needs that defense-in-depth approach. You layer controls. The guide provides a kind of security checklist for SageMaker. First, network isolation. Run everything, SageMaker Studio notebooks, training jobs, endpoints in VPC-only mode. This keeps traffic off the public internet. And use VPC endpoints powered by Private Link to connect to other AWS services like S3 or CloudWatch privately within your VPC. Build a secure perimeter.
Keep it all inside the walled garden.
Pretty much. Second, encryption everywhere. Data at rest in S3 on the SBS volumes attached to instances should be encrypted, usually using AWS KMS. Data in transit must use TLS. SageMaker even has options to encrypt the traffic between containers in a distributed training job. Third, back to least privilege. Every single component needs its own specific IAM role with only the permissions it absolutely requires. No shared roles, no overly broad permissions.
Granular roles again.
Always. Fourth, logging and monitoring. Use CloudTrail to log all API calls, who did what, when. Use GuardDuty, which has specific threat detectors for SageMaker to spot anomalous behavior. And finally, prevent leakage. Never ever hard-code credentials, API keys, or database passwords in your notebooks or code. Use AWS Secrets Manager or Systems Manager Parameter Store to manage secrets securely.
That's a comprehensive list.
Yeah.
What about performance and scale, especially for really big models or high traffic?
Right, achieving peak performance and scale. If you're training huge models or on massive data sets, you'll likely need distributed training. SageMaker offers libraries to help with both data parallelism, splitting the data across machines, and model parallelism, splitting the model itself across GPUs machines. For optimized data handling, use efficient file formats like Parquet instead of, say, CSVs. And if you have really heavy data transformations, consider offloading them to specialized services like AWS Glue or Amazon EMR before feeding the data to SageMaker.
Don't do heavy ETL in the training script itself.
Generally, no. Better to separate those concerns. For inference, model optimization is key. Use Amazon SageMaker Neo. It compiles your trained model specifically for your target hardware. A specific instance type may be inferentia, often making it run faster and use fewer resources. Techniques like quantization can also shrink the model size and speed up inference. And finally, for scalable, resilient deployment, use SageMaker's production variants. This lets you do things like A/B testing different models or deploying across multiple availability zones for high availability. And set up auto-scaling policies for your inference endpoints so they automatically scale up and down based on traffic load.
Really feels like a theme emerging here, especially when you talked about Bedrock versus custom models, is this constant trade-off. Pre-trained services versus building your own. Speed versus control. Cost versus customization.
That's a perfect summary. It is a spectrum.
Yeah.
And it raises that key architectural question. How do you guide the decision on where to be on that spectrum? Often the journey starts simple. Try the pre-trained foundation models first, maybe via Bedrock. Fast, easy, no ML team needed initially.
But maybe the answers are too generic.
Exactly. If it lacks context for your business, the next step is often retrieval augmented generation, RD. You keep the pre-trained model but augment it by retrieving relevant info from your own company documents or knowledge base and feeding that into the prompt along with the user's question.
Giving it company-specific context.
Right. That often gets you much better results without needing to actually retrain the model. But if even RG isn't enough, if you need truly specialized behavior or the highest possible accuracy on your specific domain, then you start looking at model customization on SageMaker. That could be fine-tuning an existing foundation model on your data, or maybe even continued pre-training. But this is where the cost and complexity shoot way up. You need ML expertise, significant compute resources, careful MLOps.
So the architect's job is to justify that, climb up the complexity ladder.
Absolutely. They need to clearly show the expected ROI. Why is fine-tuning worth the significant extra investment compared to RG or just the base model? What specific business outcome justifies it? That justification is critical.
Okay, so wrapping this all up, what does this journey mean for you, our listener? We've gone from the basic foundations EC2, S3, IMM, through the layers of AWS AML services, talked about team roles, and even dissected a real-world IDP pipeline example.
Yeah, and the key takeaway, I think, is that mastery here isn't a one-time thing. It's absolutely a continuous process. The guide really stresses lifelong learning. You have to keep experimenting, keep adapting, because this field moves incredibly fast.
So how do people structure that learning? Any recommendations?
Well, for a structured path, the guide points towards the AWS certifications. You could start with the AWS Certified AI Practitioner, gets you the foundational concepts across the board. Then maybe the new AWS Certified Machine Learning Engineer Associate, which focuses much more on the practical implementation skills, especially using SageMaker. And for those wanting to go really deep, there's the AWS Certified Machine Learning Specialty, which covers the advanced topics and nuances.
So certs are one path. What about other resources for continuous learning?
Oh, there's a ton. Definitely keep an eye on the official AWS blogs. The machine learning blog is essential. The open source blog often has great AML content too. Outside of AWS, there are fantastic non-official blogs, machine learning mastery, towards data science or classics, plus many personal blogs from practitioners sharing real-world tips. YouTube is huge too. Channels like Krish Nayak or Sentex have massive libraries of tutorials, and there are many AWS-focused channels run by experts diving deep into best practices. And critically, don't just read or watch do. Get hands-on. Try building something like that IDP pipeline yourself. Look at the AWS samples on GitHub. Find open source projects to contribute to or experiment with. That practical experience is invaluable.
Absolutely. So this deep dive, we hope, has given you a solid map and compass for navigating AWS. The real question now is, what aspect of this will you explore next? What boundary will you push to leverage AML on AWS?